In this video, I'm going to show you the algebraic proofs of the logarithm properties that you learned in today's lesson. So let's prove the product property. So I'm going to say let u equal log base n of a and let v equal log base n of b. Now if we change these from logarithmic form to exponential form, we would have n to the u power equals a, and we would have n to the v power equals b. Oops, that's supposed to say b. Do I know my letters? I don't know. Okay. Now, if you want to find the product a times b, you could substitute n to the u power for a and n to the v power for b. So a times b equals n to the u times n to the v. And if you use exponent properties to combine those, you get a times b equals n to the power u plus v. Now, let's take the log of both sides of this equation. Just like you could square root both sides, you could add 17 to both sides, you can take the log of both sides. So I'm going to take log base n of the left and log base n of the right. Now remember, we learned about inverse functions canceling. So when you look at the right side, you have the inverse functions log base n and n to a power. So they're going to cancel, leaving you with u plus v. So we have log base n of a times b equals u plus v. So let's substitute back n for u and for v. Remember, u is log base n of a and v is log base n of b. So we have log base n of a times b equals log base n of a plus log base n of b. Okay, so that's what we were hoping to prove. Similarly, we can prove the quotient property. So we're going to start the same way. Let u equal log base n of a and let v equal log base n of b. Okay, so rearranging into exponential form, n to the u equals a, n to the v equals b. Now this time, instead of a product, a times b, let's find the quotient a over b. So that's going to be n to the u power over n to the v power. And our exponent properties tell us we should subtract those exponents. So that's n to the u minus v. Now let's do what we did in the previous proof. Take the log of both sides, so log base n of the left equals log base n of the right. And once again, we see inverse functions canceling. So on the right, it's just going to be u minus v. And let's go ahead and substitute. U is log base n of a, and v is log base n of b. So there's that proof. So it shouldn't surprise us that the proofs of these logarithmic properties rely on exponent properties, since exponents and logarithms are inverses of each other. The third property was the power property. So if you use this letter combination, log base n of a to the b is equal to b times log base n of a. So let's prove that. So suppose I let u equal log base n of a. Then rearranging, n to the u power equals a. And what if I wanted a to the b power? That would be the same as n to the u to the b power. And using your exponent properties, power to a power you multiply. So, whoops, that's the same thing as n to the ub power. And now if I take the log of both sides, log base n of a to the b equals log base n of n to the u times b. Inverse functions cancel on the right, as we saw in the previous two proofs. So log base n of a to the b is equal to u times b. U times b is the same thing as b times u, so I can put the b first. And then substitute for u, remember back here, log base n of a. So there we have that one. And finally, the change of base formula. So you could use whatever letters you want in here. I'm not sure I remember exactly what letters I used when I did it in the notes video, but let's just pretend it was log base n of m is equal to log base c of m over log base c of n. Okay, so let's prove that. So I'm going to say let log base n of m equal k. The letters you choose for these really don't matter, as long as you're consistent. So if I rearrange that into exponential form, you have n to the k equals m. And then suppose I decide to take the log of both sides. Now I can take the log base whatever I want. So suppose I choose log base c. Log base c of the left equals log base c of the right. Now why don't we use the property that we just proved, which was the power property, and we can bring this k out to the front. So now we have k times log base c of n is equal to log base c of m. And we can divide both sides by log base c of n to isolate k. So k is log base c of m divided by log base c of n. And what was k? Remember, k was log base n of m. So if I substitute that back in, we have log base n of m equals log base c of m over log base c of n. And that's the proof of the change of base formula.